like the start of the Friday Club. You see pretty good attendance Mondays and Wednesdays, and Fridays, weekend start. Friday Club. Thanks for being here. And to that end, let us begin. So maybe a few stragglers, we can only hope. Effectively, I mean, while we left off here, it's I'm trying to present, and I did it with my class Wednesday night. I'm trying to present what's going on inside the cell without giving you some type of idea of complexity. And this has been around for a very long time. And so Harvard Cell Animation narrated, you could find it, Inner Life of the Cell. It's been around, I think it was about 2000 it came out. And what Harvard was endeavoring to do, and whoever put this together, was to try to, based on the knowledge at that time, to be able to give you an idea of kind of the complexity of the cell. The stuff that you're talking about here is not stuff that we're necessarily at all going to cover. The terminology is very sophisticated. It's based on cell and molecular biology. You're going to hear, well, but I want to give you an idea, and every so often I'll have a shout out to try to point something out. So look at that before I start really getting on with this. Really what you're going to see, even at the very end, something we had talked about, those cytokines, chemicals that are released that cause white blood cells, and you see the changes that happen. It actually causes a change inside the blood vessel with one of those embedded proteins. It kind of changes shape and helps to latch on to white blood cells and enable them kind of squeeze their way out. You see that at the very end. And you'll see the membrane and everything like that. So I do like it. I'll try to adjust the sound accordingly. Those are white blood cells. They don't latch on. On the outside. All about shape. It's more complex than what we think. Right? Disassembling and disassembling. We still Same way. It's a motor protein. Carrying one of those vesicles with that. That's the bound ribosome. This is going to be exocytosis coming up. Oh, the change. White blood cell. So, I mean, there you have it in a nutshell. The, the intricacies, all some of the things we'll discuss today, some of the things I've been alluding to, come from this. I mean, so I think it's useful. It's incorporated now into the when you're sent the videos, just to and give it a look see, or you can look anytime on it. It's quite a bit longer when they get into it, I've always just used this little relatively 7 or 8 minute clip that's there. And probably with today's knowledge, I would think that they probably have refined some of the analysis behind it. It's here, all those selectins and integrins. Don't have to know that. I'm trying to give you some context for just how unbelievably complex that interior of the cell is. You got to get the square with the circle on the board. Nah, even that one you see with all the stuff in the cell two-dimensionally. No, you've got to understand how things are constantly moving around, being constructed, being deconstructed. Some things are always there. I mean, it's an intricate network of roadways, and again, those can change as needed. Mitochondria, things can move, but they're relatively stationary in certain areas. We just get more of them when the cell is unusually busy, for instance. Which brings us to, as you remember, this is where the ribosomes were. And ribosomes are interesting. Okay, the name we give, or the designation we give to these ribosomes. Ribosomes have a large subunit and a small subunit. And you can look at it in the animation that's there, but effectively it's two pieces, and basically they as they junk together, small and large together, it creates a little spot where the messenger RNA. And it's really important down the road when you understand that why our ribosomes are different than, say, bacteria's ribosomes. We call them, it's got a fancy name after the person who discovered it, and it's part of the foundation called Stegberg. You don't know this. But the designation based on their density is called ADS. So in our cells, we have ADS ribosomes. And it's interesting, in bacteria, there's 70S ribosomes in bacteria. Interestingly, when we talked about the mitochondria, one of the things that we know it, because of its bacterial origin, the ribosomes that are in the mitochondria doing the same thing that they do inside our cells are 70S ribosomes. And that becomes it's a really significant factor in evolutionary biology. Just to give you an idea. So we were doing molecular biology, that would be part of the course. In microbe, that becomes part of the course. Okay? Just to give you some idea about how you try to build on some of these things. So here, ribosomes, non-membranous, protein synthesis. They're basically a juncture of protein and ribosomal RNA. The distinction is where the proteins are going to be used. The proteins are going to be used in the cytoplasm. If the proteins are going to make those things that are assembling and disassembling, fine. That's made by free ribosomes because they function within the cytosol, or even they make their way into other organelles. Membrane-bound ones really have three different distinctions, and you'll see this down the road. They're either made to go into vesicles. Those vesicles are either going to take their place inside the cell as a freestanding unit, or those vesicles, like you saw in the animation, are going to be spit out, exocytosed. Basically, the materials inside, rather, will be spit out, and the vesicle membrane will be incorporated with the cell membrane. The other thing, and they mentioned it a little bit in there, some of those proteins that are designed to go in the membrane will just stay in the cell's membrane. So anything, when they talk about bound ribosomes, it's to make proteins that are going to be excreted, utilized inside vesicles in the cell, or find their way into a variety of membranes. All those proteins and all those membrane functions that we've talked about previously are part of it. The endoplasmic reticulum is a series of membrane passageways that protect stuff that's being made by way of those ribosomes and other materials that are being made as they exit the nuclear membrane. It starts with the outer leaflet of the nuclear membrane, those nuclear pores that are there. So whether it's messenger RNA, whether it's a variety of substances that are going to be used, and what happens with those bound ribosomes, effectively, if they're going to make those proteins that are going to be encased in membrane for the variety of reasons I just described, what's going to happen is they form like these little studs, apparently microscopic, with little bumps. And we call that rough endoplasmic reticulum. They form right away as part of this endomembrane system. So it's a continuous series of membrane. And again, to restate over and over again because it's so important. We protect things inside the cell and encase them in membrane unless they are compatible with what's going on in the interior of the cell, which has a lot of activities and a lot of chemicals and a lot of changes in pH and the materials that are in there. And you will see it becomes, after that, we see smooth endoplasmic reticulum. And the difference is how we can get an idea what cells do. The more rough, meaning the more proteins they're making to be typically spit out, like a pancreas cell, makes insulin, constantly spitting out protein. A ton of rough endoplasmic reticulum. The liver has a ton comparatively of smooth endoplasmic reticulum. There's always some of both. That's because the liver does, big role the liver does, processing fats and detoxification. Nearly all of those substances are fat compatibles, and that's where they do it, within the smooth endoplasmic reticulum that is a variety of chambers surrounded by these fats that are able to do the processes and other roles that they play. So here's what it looks like. This is the start of the endomembrane system, the nuclear membrane. The pores feed into it. Here you can see those little dot-like structures that are there. And so when we see them with stains, they had a rough appearance, and they were defined as rough endoplasmic reticulum. It's not a textural thing. It was just a visible thing and an easy way to describe it. Now you can pass your finger over it and say, oh, it's got little bumps in it, microscopically. It appears rough because it's studded with attached ribosomes, proteins that will be secreted, proteins for plasma membranes, other stuff, phospholipids, part of the membrane. Okay. A cistern is a well. It's a name you're going to see. So the old-fashioned term for well was cistern. And so these cisterns are really sort of little cul-de-sacs of membrane this stuff stays into. Down the road, you're going to see it's extraordinarily important how your muscles contract. Okay, those wells are filled with calcium ions. And every time your muscle moves, there's a massive release of this calcium. And every time your muscles relax, it gets pumped back in. Notice the word pumped, back into those wells for storage. Continuously. So, and then eventually it's sent to the Golgi apparatus, which is nothing more than the packaging and shipping department. A lot of intricate things goes on. They talked about glycosylation and stuff like that. Effectively, it's modifying those materials to the form that there should be in, so they can be easily released or utilized for wherever their destination is. Whatever analogy works for you should be straightforward. We're not we're not going to do intricacies of it. You're going to see cis and trans. We're not going to do that part of it because it has directionality as to where it's coming from or where it's going to. Here's the smooth. Continuation of the rough. Enzymes found in plasma membrane, which are very, very similar to it. So those are some of the integral proteins. What happens there? Lipid metabolism. This is where the cells make those components that are lipid-based, and lipoproteins plays a role a lot in fatty metabolism. That's there, and that's why the liver is filled with this stuff. Okay, detoxification. Liver is filled with this stuff. That's why the tragedy when someone's liver is damaged. Okay, that these vital functions are destroyed. I mean, I can't tell you how important it is. You're very concerned about that today. And unfortunately, many of you who go into clinical fields people have damaged their livers for a variety of reasons. And certainly the most common is alcohol abuse. But a variety of things. Drug use, drugs themselves, certain kinds, hepatitis. There's a variety. Hepatitis is not a universal term. It's a viral. Typically, infectious hepatitis is viral in orientation. They're not the same virus. There are many of them that are there. I know that's, again, something you talk about in micro. Alcoholic hepatitis is more of a substance related. There's a variety of other things. Different kind of poisons will do it. Glycogen, this is the source, again, in the liver, underscoring the importance, where glycogen is able to be released as free glucose. It's your emergency sugar supply. Basically, when your body's in a stress reaction, and you're going to hear the name sarcoplasmic reticulum. That is specific to muscle cells. Sarco is the prefix when we get to the cellular or molecular level of skeletal muscles, of all muscle cells, rather. Very, very specialized part of this skeletal and cardiac muscle. We'll really explore it in skeletal. Okay. Here, Golgi, the continuation of this endomembrane system. All sorts of these sacs that are sort of squished together. It's like you have a whole bunch of plastic bags and you kind of, it's like you go to the grocery store and they're all there. I hate that. Because every time I try to pull them out, they get stuck. It's a pet peeve of mine. You're hearing I have a lot of these pet peeves. I just do. It's like when I'm ready to sit down and watch the game, that's when the dog has to go out. That's when the cat has to annoy the dog. You can't make the stuff up. That dog, if the Steelers are first and goal, that dog has to go out. Maybe it's the shirt I put on. We digress. 3 steps. Yeah, everybody liked that one. I haven't used that one before. It's a new one. Thanks. I'm really impressed. I love this class because you guys show up all the time, which is encouraging. Not that encouraging. Don't make a habit of it. So, again, they transport the stuff in, and this is the cis is the interface. We use the term cis and trans a lot now today, in a social context. But cis is the interface, trans is the outer face. Don't have to know that. Okay, SAC, tag, sorted, package, traffic director. Pick one that works. Oh, you always see the image that looks like this. I'm not going into it. In cell and molecular biology, the instructor, my colleague, Dr. Hillwood, she goes into it in vast detail. She's probably doing it now next door. And you can see this what it looks like from a electron microscopic, and you can see the size 90,000 times enlarged. And what it does, these vesicles, the ones that we call secretory vesicles that I talked about before, okay, the ones with the V snares and the T snares, proteins to be used outside of the cell, and they fuse with the plasma membrane, and effectively it's excreted. The other vesicles containing a variety of stuff fuse with the plasma membrane or the organelle and go right into that membrane. They're part of the membrane-bound proteins. And the other pathway is it contains the enzymes we use for digestion and defense. And so that becomes effectively a new lysosome, or what you'll see shortly, a new peroxisome. So they're all different kinds of things that are there. They're showing you the different ways it goes. You can look at the graphic here. I don't bother to read this, but you can see it. It's just pointing out the different destinations. Not a lot to say about it, but you can see there's a lot of information here. And you can read that as well as I could read it to you. Lysosomes, we talked about in the context of what happens. Anything that is brought in by endocytosis, effectively, any of those vesicles, whether phago or pinocytosis or receptor-mediated endocytosis, they're going to fuse with a lysosome and be interacted with, other than the ones that are going to go straight through. That's transcytosis. These are different. They are much more about defense, very, very little about digestion. If anything, they do play a role in some aspects of fatty acids. That's less of a role. Which brings us to a really important topic, free radicals. Free radicals are the crux of modern cancer theory, modern aging theory, tissue degradation, cellular degradation. These are, down the road, you hear about something, and again, it's in micro, about what are called initiators and promoters, things that start damage and things that continue damage. Alcohol would be an example of both. Cigarette smoking and the problems associated with the carcinogens in there. What makes them carcinogens is they start to damage tissue and they promote the damage. Most of the way they work are through free radicals. What are they? Any aerobic organism like us, any cell that's aerobic, has to have a means of dealing with problems, because when we utilize oxygen, there are problems that are associated with it. Oxygen, you saw me do a little more come up here like this. Let me have to turn the lights every go like that. Scatter. You talk about that later. So what happens with oxygen? The whole idea of oxygen is so you take a carbohydrate, you don't have to write down, just listen. Plus oxygen, I'm balancing the equation. And yeah, we wrote this before. The basic metabolic reaction. Oxygen, I told you, was sort of the ticket to get into the, basically the ticket to get into the mitochondria. The idea is that we have these wonderful carbohydrates that are rich with carbon to carbon and carbon to hydrogen bonds. Okay? Fats are even better because they don't have a whole bunch of OHs to show up. So they're filled, those covalently sheared electrons are filled with energy. We want to suck the energy out of them. This wonderful pair of electrons, separate them, that release the energy. Separate them, release the energy, and voila, we suck it up. The problem is, now that we got the energy and transform it to ATP, what about the electrons? You've got to have a parking place. Oxygen has got a fancy name called the terminal electron acceptor. It's the parking place for all those electrons. If you take a half of an oxygen molecule, just go. There's a lot of electrons out there. They probably don't have a half oxygen lingering around. And remember, oxygen has a valence of 2. That means it wants 2 electrons in this case, in the worst possible. Maybe your electrons are 4, you're not all electrons. Nobody cares. So you add 2 electrons, okay, and what do you end up with? An O with a -2 charge. A happy oxygen. Now, how do you complete it, make it really happy? This is all that energy, all of those electrons being zapped of energy is in the proton motive force. What do we have a lot of with that? Protons. That's the name. Take 2 of those protons, get it, and make our favorite waste product, water. So the whole idea in a perfect world, all those electrons that are bombarding oxygen would be sucked up, matched with 2 protons, and you have water, which we can deal with. It's not a toxic substance. The problem is this: it's being bombarded. It would be naive with the trillions of molecules that this is going on constantly, that like that periodically you're going to get one of these bad boys. It's called a free radical. It's an unpaired electron. This one is called super oxide. What it does, what free radicals do, is they go into and they effectively contact is the wrong word, bump into otherwise stable molecules and destabilize them. As this goes on, eventually it leads to instability on a cellular basis and an interior on a molecular basis, and it starts the framework of changes that are going to cause damage over time, whether it's cellular damage, whether it's damage in mitosis, that's where you start to get into a cancer, whether you're doing damage to the ability to replicate, maybe that's where you start to get things that are associated with aging, and it starts early on. The more of these things that cause free radicals that you put into you, they have an additive effect. We have enough of these peroxisomes to cope, and other mechanisms to cope with it, as long as we don't go over the top. What you're going to find out, and it gives you the answer here, these highly reactive molecules are a natural byproduct of any oxygen utilization system in any organism. And havoc is a good word, if not detoxify. They are the most toxic. There are other ones. We actually start with something called an oxidase. Okay? Okay, and what it does is it uses oxygen to convert the toxins, and it's got a fancy name called superoxide dismutase. You don't have to know about it right now. And it changes it to hydrogen peroxide. Everybody knows what hydrogen peroxide is. Hydrogen peroxide happens to be also something that has free radicals. And I know they sell it, and you can go into Giant Eagle, you go into any pharmacy in the world right now, you probably have it at home. And why do we use it for? We use it if we have a scrape or a cut, or for some kind of wound care. Okay? and you put it on skin by itself, doesn't really have an effect. But if you put it on any kind of an open wound, and even minor little scratch, or any type of interruption in the skin, what happens? Get back to the chemicals that are inside the cell. Cells are disrupted. It releases those chemicals. One of the chemicals is called catalase. All of our cells have it. And catalase rapidly changes hydrogen peroxide to water and oxygen gas. So what happens if we put it on skin that's not intact? It bubbles. Okay, that's forcing oxygen, and that's what the bacteria don't like. They have limited coping mechanisms for excessive amount of oxygen. Good news. Bad news is it's pretty darn strong. It's a vicious reaction. It stings. You want to know the right way to use it when you're at home? If you're going to use it on a wound like that, dilute it. Just get any kind of water. Distilled water, regular water would be fine. Filtered water, about 1 to 10. An ounce to 10 ounces. Put it into anything. A glass, a spray bottle, and use that. A lot of these things, betadine's the same way. You should be diluting them. But again, that's to me, that's part of my micro lecture series. But I'm giving it to you because thankfully all of you won't be with me for micro. Moving on. So the peroxisomes do all that. Okay? Very, very important. And you're going to see vis-a-vis why it's so helpful for microorganisms. They have very limited, much more limited capability than we do. The bottom line for this sort of long-winded explanation is really, I think, an important part, is to understand that the more of these things that you, either your activities, your lifestyle, what you ingest, the products that you use over time, it's a numbers game. How many of you have limited resources to deal with them? We have plenty. But if you overtax any system over time, it's going to be a problem. Why do folks why do people in radiology wear badges? They wear badges with a little bit of film in them, okay? So they don't get too many x-rays over, and you check them. I did in my office. You send the badges in once a month, and they tell you, have there been, there's a little piece of film that's in there. Have they been exposed to too many x-rays? They better stay away from it for a while. You document that. Why? Because if you are exposed to too much over a limited period of time, it has the potential to cause cellular damage. What's it doing? Releasing free radicals. Those x-rays are something you'll come to know are called ionizing radiation, making charged particles. Got it? Moving on. The lysosomes, mostly digested, hydrolases, probably, and they call them a safe site because they're involved. Again, they're contained there. What happens when you hurt, cut yourself, twist an ankle, name it? Cells are disrupted, lysosomes spill out this stuff. It's nasty. It starts irritating everything, summons white blood cells, makes it nastier. It's somewhat of a vicious cycle until it gets under control. Yes, it gobbles up the bad guys. Yes, it takes care of organelles. Like I said, organelles have a lifespan. They're not there forever. There's constant turnover. Breaks down, releases glycogen. When we get to bone, you're going to see the importance of all this. Plays a role in something we call autolysis. When cells are no longer functional, we're recycling cells constantly. I'm sure I've told you, billions of cells every day are shed and made. In your gut alone, stomach, small and large intestine, the entire lining, all those wonderful simple columnar cells you learned about in lab, you replace them all every 3 to 6 days. All. It's a lot of cells. Voila. Yeah, fine. Safe sites. Got that. I commented on this before with regard to genetic problems. Lysosomes are great, but when they accumulate too much garbage, it's a mess. Think of the place where you go by a house and all the garbage is piling up. You go, oh my God. That's got to be a minefield for rats and other nasty stuff and disease. This is called Tay-Sachs disease. It happens because you can't break down a particular enzyme in the lysosome, glycolipids in brain cells. And what happens is the baby, over time, they accumulate to a certain point where they cause deterioration. And I told you, a baby, first 12 to 18 months, normal, flourishing, and all of a sudden, down. but somewhere between age 2 and 5, they succumb. It's a nightmare. It's a genetic disease. Again, my first wife and I were tested for, and thankfully we're not found to be carriers. Unfortunately, it didn't have the opportunity, unfortunately, to have children biologically that are there. And here's the endomembrane system. The other nugget about this continuous passageway from the nuclear membrane, endoplasmic reticulums, rough and smooth, Golgi apparatus, vesicles, lysosomes, plus the plasma membrane. And all of the thing they do, they work together. Whether it's for production, whether it's for control, whether it's for emergencies, whether it is for degradation, or all of these things. As long as everything is working properly, the interior of the cell is kind of a happy place. And these are all things that those of you going into patient care, no one is going to ask you what the Golgi apparatus is. I'm willing to wager that. No one's going to ask you how you did in micro or AP1 data. All they care is how well you take care of them, honestly. The doctors, a little different. Okay? They like to see all that stuff on what we call the ego wall. The 63 certificates that are there. Half the time you go to a conference, they give you a certificate and stick it up on the wall. So don't make more of it than what it is. Okay, I have them in a box in my office if you want to see some. About the 3 that matter. So what I'm telling you is, I'm trying to give you an idea of how these things are happening. If someone wonders, why am I back here in the hospital? And you start, and I'm not telling you to give them a temperance lecture, in other words, to stop drinking, but to try to give you an idea of maybe there's a way that you can interact with them. Start to maybe set their mind in the right direction. Boy, it's great to do it this indirectly. We had a friend of the family, boy, he drank too much, ended up having liver. Even if you're, how should I say, using creative thought waves. I'm not telling you to tell falsehoods. That would be wrong. But find a way. Or we learned about that in class. Our stupid teacher in A&P and all these stupid things he told you about. It's okay. I'll take the hit. I'm good with that. Maybe this is helpful. I don't know. I'm trying to remember.
The secretory protein is synthesized inside the rough endoplasmic reticulum, migrates through it, and exits inside the vesicle. The vesicle travels through the cytoplasm to the Golgi apparatus. The Golgi apparatus modifies the protein. The protein is dispatched from the Golgi in a transport vesicle that then fuses with the plasma membrane, releasing the protein to the outside of the cell.
Yeah, got it. Not great. You saw, that's why I like the animation first. Elaborate networks of rods. The ones that are there consistently are called intermediate filaments. You remember those, or you should, with regard to desmosomes. They are reinforced by intermediate filaments, mostly made of keratin. Structural strength. They are insoluble by nature. Most of them are what we call tetrads. So it's braided with 4 simple units that create like a 4-unit braid. Okay? My wife doesn't do braids. She got those hot rollers, baby. I wish I could do that. Opportunity for laughter. I wish I could do that. For those of you who are awake, thank you for smiling. The microfilaments are made of actin, a very interesting protein that's part of the framework of every skeletal muscle in your body. Absolutely vital to understand. When it's disassembled, it's soluble. When we assemble it, it's insoluble. So that's what I mean. Those thread-like filaments that can assemble and disassemble allow your cells to basically do amoeboid motion. The larger version of these that are responsible for the spindle, so famous in mitosis, for things like cilia and flagella, are called microtubules. They're made of a protein called tubulin. It's not an overly creative naming. Again, and it's more of a hollow tubule where actin is really not. And again, just like during mitosis, they form to create that spindle, and then when mitosis is done, okay, they disappear. So here are the filaments, thinnest of all. Microfilaments are the thinnest. Tubules by diameter are the thickest, or have the greatest diameter. The intermediate filaments are a bit different, but they're in between, hence the name intermediate. So protein is actin. Yeah, they're underpinnings of sort of have a little bit of an impact on the surface of the cell and the shape. Cross-linked networks attached to the cytoplasmic side. Motility, that's being able to amoeboid motion. Endocytosis and exocytosis, they're extraordinarily important. Our cells, as you could see from the animation, it's very realistic. It's an extraordinarily busy place. It reminds me of one of those, like the sci-fi things where you start to see these cities, all things flying around, like being very 3D. It's like when we first saw a couple of the, when we started with Star Wars. Well, everybody, Spaceballs 2 is coming out in 2 years. I hope to be here to see it. I hope Mel Brooks is here. You'll love it. That was his parody on Star Wars. Actin, here it is. Typical conformation looks like a double string of pearls that are there. When it's like this, it's soluble. When they disassociate, it's not. So they're made of the actin subunits. Intermediate, tough, insoluble, rope-like protein fibers. The tetramer, 4 fibrils. You're going to start to see terms like fibrils and filaments, fibers. They have different meanings. Be watchful of those. So I'm just asking you to know that it's basically it's fibrils and it's twisted together. Very strong desmosomes, internal guide wires, and we see them in a lot of different types. So keratin filaments and epithelial cells, that's what your skin's made of, keratin. Okay, neurofilaments. There's a very intricate passageway for neurotransmitters to flow in nerves. There's also an intricate passageway for things that are reabsorbed to go backwards. It's very interesting when you get to the nervous system. That are there. There's a way of looking at the way that sort of the representation of this and how small it is, 10 nanometers that are there. And lastly, the microtubules. The tubules, again, tubulin, a little bit different. They described it in that it's sort of an oval or ovoid kind of, I don't care about the shape in that. And they mostly come from the centrosome. It's near the nucleus, okay? And you're going to see it producing, and the fancy name that you're going to see when you get to mitosis and meiosis are centrioles, and effectively they produce these when it's necessary to do that, radiating from there. Organelles are tethered to microtubules. It doesn't mean they can't move. Being tethered is like anything else. It's like we tie out the dog sometimes. We got a 30-foot line. He's tethered, but we have a big backyard. And he's, big dog, big backyard. So he goes out there all the time, chasing a variety of animal life. Goes out there. So, and they are moved through, and you saw the motor proteins, proteins that change shape, motor proteins. This is sort of the design, the way it's assembled. It's sort of a spiral-like design, as you can see from the illustration, but you can see the sort of the hollow nature within that's there. And the motor proteins change shape. Big deal for that. Here's the centrosome, cell center. With mitosis, we're going to see something called centromeres. That's an area where the chromosome pairs attach to the spindle. And so the centrioles are with a barrel shaped. Where it comes from, right angles, not a big deal. Radiate. The big deal is cilia and flagella. It's going to be the last topic for here. So the centrioles, and this is very interesting. Again, one of the areas that support evolutionary biology very well are these structures. In bacteria, at the base of any of the flagella that protrude, okay, any of their structures that protrude, so to speak. Flagella is the wrong word, but they have what's called the basal body. And this has this classic 9, we call it a 9+3. It's a pinwheel with 3 microtubules sort of grouped together and nothing in the middle. It's a 9+0, I figured. That is there. 9+0. That's a classic basal body, and we will see this even in bacterial cells as well as our cells that are there at the centriole. When we actually see cilia or flagella in our cells, okay, when we see cilia and flagella in the tiny cells, the single-celled organisms we call protozoan, that many of you looked at in pond water previously, okay, they have the same arrangement. The cilia and flagella, which help things move. Microvilli are a little bit different. When they say they're cellular extensions, it means that, again, the proteins are on the inside and they're pushing out and they're encased in membrane. So it's not as though they're out there sticking out, protruding like hairs. They have a fine sort of membrane coat around them. And the cilia and flagella, cilia move in a whip-like action, moving mucus around, stuff like that. Flagella we only see in sperm cells, and whether you want to meet that as a cell or not, but it's only obviously in the male. They're made up of microtubules, come from the centrioles. They're attached to those basal bodies, which have the 9+0. Okay, and the 9+2 is the classic pattern of what's protruding from them, the cilia and the flagella. And you'll see it here, 9+2. And again, we see that in a protozoan. And you'll see evidence of this microscopically again when you get to microbes, again to support a lot of the evolutionary biology theories. Here you can see the membrane encasement. This is how it moves the mucus. They're like oarsmen. And it's very, very interesting. Everything is sort of this kind of an action. It's not like a propeller or anything like that. It's very much a whip-like action. And I make that point because there's a distinction between the way a flagella works in bacteria and the way it works in our cells. And I'm not doing that illustration. So the microvilli are just really little extensions these are made by actin filaments. And this is where you see the indigestive cells are all like. This is all surface area. You see indigestive. Enough. Save the nucleus for another day and time. We'll view the nucleus, and there's not a whole lot left to say about it. Have a great weekend. Enjoy.